Bismillahirrahmanirrahim. Assalamualaikum warahmatullah. So today we will discuss about chapter 2, part B, analog modulation, in particular frequency modulation, FM. So this is the chapter guideline. As a reminder, so we have done part A, amplitude modulation. Today we will discuss part B, frequency modulation, which include introduction, the analysis of FM equation, and some discussion on commercial broadcast and comparison between FM and PM. The scope, the outline of the chapter, the definition of FM, calculation of voltage, modulation index, power, and so on. Calculate and draw FM in time and frequency domain, and also the bandwidth. Define and describe mathematically angle modulation. Calculate the deviation and percent modulation. And lastly, compare the advantages and disadvantages of FM, AM, and PM phase modulation. Okay, so frequency modulation. We have seen this slide before. Frequency fall into angle modulation, which is another technique that can be used in modulating signal. Okay, so to change frequency and phase of carrier signal. So angle modulation, there are two type of modulation under angle modulation, which is frequency modulation and phase modulation. So changing the frequency produces frequency modulation signal, FM. Changing the phase of carrier signal produces the phase modulation, PM signal. So this is a general overview of angle modulation, where you have frequency modulation and phase modulation. This is the modulating signal, and this is the carrier. So we have the modulating signal and the carrier here. So the difference is that between frequency, the difference of the FM and PM signal is the FM signal changes in terms of the frequency depending on the amplitude of the modulating signal, where the output of PM changes in terms of phase when the modulating signal changes in terms of amplitude. We will discuss this further later on. So angle modulation focus on phase deviation, how much phase shift the carrier signal undergo compared to the original carrier signal phase in radian, phase shift or phase deviation. So in frequency modulation, FM, the important features about FM waveform are: first, the frequency varies or the frequency changes, but the amplitude remain constant. Second, the rate of change of carrier frequency changes is the same of the frequency of the information signal. Okay, the rate of change of carrier frequency is same the frequency of information signal. So the rate of change depending on frequency of, what is this? Modulating signal. The amount of carrier frequency changes is proportional to the amplitude of modulating signal. Information signal is also known as modulating signal. So number 4, in frequency modulation, the amplitude of the signal is constant. The amplitude of the FM modulated signal is constant. So this is the general showing the signal of carrier signal, modulating signal, and the output of FM modulated wave. So we can see here, this is the carrier where you have constant amplitude and constant high frequency. This is carrier, constant amplitude and high frequency. And you have here modulating signal, a changing amplitude and also changing the frequency. So the output for FM signal, where when the carrier wave and modulating signal combine together, we will have constant amplitude here, but the frequency changes. The frequency varies according to what? So we can see that here, small amplitude of modulating signal result in low frequency in FM signal, FM modulated signal. Small amplitude or low amplitude, low frequency. Here it shows large amplitude, here large amplitude, the amplitude of modulating signal large, result in high frequency in FM signal. So we can say that small amplitude of modulating signal will result in low frequency, and large amplitude in modulating signal will result in high frequency signal. High frequency in FM modulated signal. This is the comparison between FM and AM. So we can see here, this is the modulating signal, where you can have a low frequency and a constant amplitude. Okay, so we can see here the output, the AM modulated signal is in the envelope. Okay, hopefully we still remember the envelope of AM signal. So the envelope has constant frequency, same as the carrier frequency, but changing in terms of amplitude. This is AM signal. However, for FM signal, it has constant amplitude, same as the carrier signal, but the frequency changes. We can see that the frequency here is proportional to the amplitude of modulating signal. You have high amplitude, high frequency, high amplitude, high frequency, low amplitude, low frequency. Okay. FM analysis. So this is the mathematical part of FM signal. So let's assume that we have a carrier signal with this equation, VC T equal to VC cos omega CT. So VCT is the carrier signal in time domain. VC is the maximum amplitude. Cos omega C is the frequency of carrier signal. Omega is 2 pi f and T. And likewise, we have the information signal, also known as modulating signal, VM modulating. Vmt equal to Vm. Vm is the maximum amplitude of the modulating signal. Cos omega mt. Cos omega m is the frequency of the modulating signal. Omega is 2 pi f. In FM, frequency changes with the change of the amplitude of the information signal. In FM, the frequency, this frequency, changes with the change of amplitude of information signal. Amplitude of information signal is Vm. So we will see how this Vm can change this omega c. Okay, the instantaneous modulated frequency, let's say omega equal to omega c plus kVmt. So what is this? This is the frequency of the FM signal, is the sum of frequency of the carrier plus k, and this is the signal of the this is the modulating signal. So we likewise the frequency in terms of f here, so we divide by 2 pi. So this same equation, divide by 2 pi, we have f. Instead of omega, we have f. F equal to fc. F is the frequency of FM signal, equal to fc, the frequency of the carrier, plus k Vm. This is this equation, divide by 2 pi, Vm cos omega mt over 2 pi. This part divide by 2 pi. So at the end we have fc plus delta f cos omega mt. So this k Vm over 2 pi, we change into delta f. So delta f is k Vm over 2 pi. K is the constant of proportionality, and delta f is frequency deviation. Delta f is k Vm over 2 pi, which is frequency deviation, and k is constant of proportionality. K is constant. Simple. K is constant. Constants of what? Constants of proportionality. So from this equation, we can also say that delta f equal to kf Vm. So kf is frequency deviation constant. Kf frequency deviation constant in unit of Hertz over volt. So the derivation of the equation, Vm equal to Vc cos theta. So the theta is obtained from the this is integration of omega dt. So solving this integration, we have omega ct plus kvm sine omega m sine omega mt plus pi. So assuming pi equal to 0, Vm equal to Vc cos omega ct plus k Vm over omega m sine omega mt. So this is the equation where we discussed just now. So we can write the Fm equation as Vc cos omega ct plus mf sine omega mt, where ms is the modulation index of Fm. Okay, mf is equal to kvm over omega m equal to kvm over 2 pi Fm. So omega is 2 pi f. Omega m is 2 pi fm. So delta f is kVm over 2 pi. So from this equation, we have the formula for modulation index, which is mf. M is the modulation index, f is the fm. Modulation index for fm equal to delta f over fm. Delta f, frequency deviation over fm, the frequency of modulating signal. In the fm, the value of modulation index mf can be any value from 0 to infinity. So mf can be any value. So let's see the frequency deviation. The highest frequency for FM wave is Fmax, which is Fc, the carrier signal, plus delta F, change of frequency. The minimum frequency for FM is Fmin, which is Fc, the carrier frequency, minus delta F, change of frequency. The total change of the frequency from minimum frequency to the maximum frequency is called frequency carrier swing, FCS. FCS equal to 2 delta F. Basically, FCS is Fmin minus, Fmax minus Fmin. So Fc minus Fc, this one delta F plus delta F. So we got 2 delta F. So this is called a frequency carrier swing. This is similar to bandwidth in amplitude modulation. Okay, so in this FM we call it frequency carrier swing. So this figure shows the concept of frequency carrier swing. So to show how much the frequency is changed compared to the original carrier signal, we use frequency deviation. So relative displacement of the carrier frequency compared to the original carrier signal frequency in Hertz. So we have the carrier frequency here, and it swing to the max to become Fc plus delta F, and it swing to the minimum become Fc minus delta F. So the frequency at maximum when the amplitude of modulating signal is plus Vm, and the frequency is at the minimum, Fc minus delta F, is when the amplitude of the modulating signal is minimum at minus Vm. So we will have this full delta swing from Fmin to Fmax, which is equal to the value of delta F, this one, and another delta F, this part. So equal to 2 delta F. So the value of Fmin to Fmax is equal to 2 delta F. So this figure shows a little bit clear about what the concept of frequency deviation and frequency swing. Okay, example. Let's see one example. Determine the peak frequency deviation, okay, delta F, and modulation index MF for the FM modulator with a deviation sensitivity K and modulating signal Vm 2 cos 2 pi 2000 T. So from this, how to solve this equation? Just use the formula Okay, we have the value of K, we have the value of omega, and we have the value of Vm here. Vm, Fm, or omega m. Sorry, Fc, so Fm and omega here. Number 2, determine the peak phase deviation of a PM modulator with a deviation sensitivity K and modulating signal Vm. 2 cos 2 pi to 2 kt. So same, we can use the formula also to solve this problem. Delta F equal to K, we have the Vm, and we have omega here. Okay, you can try first. We will discuss the solution the next slide later. Okay, that's all. Thank you very much for your attention. Okay, bye.